blast radius, breaking the radius protocol with chosen prefix MD5 collisions. The talk will be given by Adam Soul. Adam is a PhD student at UC San Diego, advised by Nadia Henninger, which Keegan and I are, of course, completely impartial about this paper, being also advised by Nadia. But Adam is, in addition, also advised by Daniel Micancio. And he is interested in lattice cryptography and mathematical cryptanalysis, and especially the combination of the two, lattice cryptanalysis. However, this paper here is not lattice cryptanalysis, it is MD5 collisions. And yeah, we just couldn't resist to have this paper at WAC. So please, Adam, take it away.
Thank you. Right, let's make sure that this, excellent. So yes, I am Adam Soul. I am presenting on the blast radius attack. This is joint work with Sharon Goldberg, Miro Haller, Nadia Henninger, Mike Milano, Dan Schumo, Mark Stevens, and myself. Our attack allows a network adversary with a machine in the middle to forge arbitrary radius responses. This means you can log into a device that's using radius with completely bogus credentials. This is not a vulnerability in any particular implementation. Rather, this is a vulnerability in the radius protocol itself, namely that it uses MD5 for authentication in the year 2024. But let's back up a little bit. What is radius? Radius is the protocol for authentication, authorization, and accounting, or AAA. Let's say you have a device that you want to be able to log into over the network. But you don't want to handle authentication on the device. Instead, you'd like to outsource that to some separate server. What you can do is you can have the device and the server speak radius to each other in order to have the device be able to know whether any particular login should succeed or fail. The user logging into the device happens over any protocol you want, HTTP, SSH, whatever. That part isn't radius. Radius is specifically the conversation between the device, which acts as a client, and the server, which is, of course, the server. A surprising number of things use radius. Basically, every piece of networking equipment manufactured in the last 25 years uses radius. This includes administrator logins to internet backbone routers, logging into VPNs. Basically, every non-cable ISP uses this internally. Identity providers like Okta and MFA providers like Duo use radius as one of the supported ways of integrating with their services. And although it's not vulnerable to our attack, Eduroam and other enterprise Wi-Fi networks use 802.1x, which in turn uses radius. And it's not just networking equipment. It's also power grid equipment and industrial control systems. Radius is sort of a standard for such devices for being logged into over a network. So even if you yourself don't use radius, your infrastructure, be it network or power, almost certainly does. Radius has been around since the 90s, and it is using cryptography from the 90s, in particular MD5, which was broken almost exactly 20 years ago. I think it was the 16th, so nearly exactly 20 years ago. It is still in use to this day because, for one thing, it is really hard to deprecate MD5 while maintaining backward compatibility with devices that are still using it. But also because among practitioners, it was known that MD5 was broken, but it was not known that MD5 was broken in the precise way that it's used in this protocol. To quote this IETF draft from last year, it is a testament to the design of radius that there have been, as yet, no attacks on radius authenticator signatures which are stronger than brute force. So in this work, we present an attack on radius authenticator signatures that is stronger than brute force. Let's take a closer look at how radius works. A user tries to log into a device. Again, this is over HTTP, SSH, whatever. The device then sends an access request to the server, saying, hey, server, here are the details of an attempted login. Should I allow this login or not? The server then replies with either an access accept or an access reject. And this is what determines whether the device lets you log in or not. There's another response that the server can also send, which is access challenge. This basically extends the conversation longer between the device and the server and is used for challenge response authentication and other authentication modes. But we're mostly going to focus on access accept and access reject. This conversation happens over plain UDP almost all the time. In order to authenticate packets, in particular responses, there is a shared secret that the device and the server are configured with when the network administrator is setting the device up. And it is static from then on. Hopefully, it has enough entropy. And it is used with this sort of custom MD5-based construction to authenticate the responses and also to obfuscate passwords. Entertainingly, the password obfuscation in at least one of the authentication modes used with Radius is a custom MD5-based encryption scheme. And yes, I said that right. It's encryption, not hashing. That part is a little terrifying, but we're not even looking at it in this paper. Taking a closer look at the packet formats, access requests, and in fact, all of the Radius packets include a 4-byte header that says what type of packet it is and the packet length, and also a counter that's used for matching requests and responses. Access requests then include a 16-byte random string that the standard calls a request authenticator, but since it does not actually authenticate the request, we call it what it is, which is a nonce. It then contains a list of attributes. And attributes are a variable length sequence of type, length, value pairs that can be things like the username, the password, the IP address of the device being logged into. There's a number of vendor-specific attributes as well. The responses, accept, reject, and challenge, also have a list of attributes. Here we can see that the access accept can have a welcome message and also something that sets the privilege level when you log in. But instead of a nonce, they have a response authenticator, which is this MAC construction based on MD5 that is intended to protect the packet against forgery. So let's take a closer look at that. In order to compute the response authenticator, the server modifies the response packet to include the nonce from the request that it is a response to. It then appends the shared secret onto the end and hashes the whole thing with MD5. So that's the header from the response, the nonce from the request, the attributes from the response, and then the shared secret, all of that MD5. So quick poll of the room. Who thinks that this is a secure MAC? That's right. This is not a secure MAC because if you find a collision between a pair of messages, which is easy to do for MD5, then their MACs will also collide because MD5 is it follows a Merkle-Damgard construction and outputs its entire internal state. So once the internal state collides, you can append any suffix, and as long as it's the same suffix on both sides of the collision, the result will still collide. As just sort of a fun side note, what if we had done the secret in front of the message? Who thinks that would be secure? No, that's vulnerable to length extension attacks. What if they had done both? What if they did secret concat message concat secret? Who thinks that would be secure? Who thinks that would be insecure? Entertainingly, this actually turns out to be secure with a few caveats. This is an example of what's called sandwich MAC or envelope MAC. And as long as it is padded correctly so that the secret falls on a block boundary, this actually can be shown to be secure under similar assumptions to HMAC. And MD5 seems to satisfy those assumptions. HMAC MD5, we don't know how to break yet. And similarly, sandwich MAC MD5, I believe we don't know how to break yet. But that's just sort of a fun side note. So in our attack, we are an attacker with a machine in the middle between the Radius client and server. We want to forge an access accept because this is what will let us log in no matter what credentials we include in our login attempt. But we don't know the shared secret, so we can't compute this response authenticator. What we can do is we can create a collision such that we have a reject packet that we think we can get the server to send us. We have an accept packet that is the one we would like to forge. And if we can get those to collide, then certainly appending the same shared secret to both of them will still collide. Then if we trick the server into sending the access reject side of the collision, then we will be able to copy that response authenticator onto the accept packet, and it will be valid. So to sort of summarize, our attack starts by trying to log into the victim device with completely bogus credentials, and the device then sends an access request. We're going to intercept that request and compute a collision between a pair of packets, one of them an accept, one of them a reject, where we don't know exactly what the response authenticator will be, but we know it will be the same for both packets. We then send a carefully crafted request to the server that causes it to reply with exactly the reject packet that is in our colliding pair. It's going to include the response authenticator, which we can copy onto the access accept packet. And now the victim device sees an access accept packet that has a valid response authenticator on it, and thus lets us log in, even though we've used completely bogus credentials. So that's sort of the high-level overview of our attack. Let's look at the details. So first, some context for MD5 collisions. MD5 has been known to be weak since 1993, but the first full collisions were found in 2004 by Wang et al. And this is a collision between unstructured strings of gibberish. More useful for attacks is what's known as a chosen prefix collision, which is where the attacker gets to choose a pair of prefixes, P1 and P2, and the collision process finds gibberish G1 and G2 such that P1 concat G1 collides with P2 concat G2. As mentioned earlier, with MD5, you can append any suffix s to both sides of that, and the result will still be a collision. This was used by Stevens et al. In 2009 to produce a rogue TLS-CA certificate. And then for about 15 years, cryptanalysts worked on more interesting things like SHA-1, and MD5 was basically considered dead. Until now, when in 2024, widespread protocol like Radius is still using MD5, which is we were especially surprised by, since MD5 has been known to be weak since around the time I was born. So we can use this chosen prefix collision in our case by predicting the prefixes for the accept and the reject part of the response authenticator computation. So we can have the accept header and accept attributes that we'd like to forge, the nonce from the request. We concatenate gibberish onto the end that makes it collide with the reject header and reject attributes we think we can get the server to send us, along with the request nonce, with reject gibberish concatenated onto the end. And of course, there is a secret that comes at the very end that we don't need to care about because it's the same for both. So this is how we can apply a chosen prefix collision to the specifics of Radius. But there's a number of challenges here. The first challenge is that we don't know the nonce until we see the request, which keeps us from pre-computing this collision. Instead, we need to compute a collision online in real time after we intercept the initial access request. Now, you may think that's not a big deal. MD5 collisions can be computed in seconds. We don't need to worry about the client timing out. Unfortunately, the MD5 collisions that can be computed in seconds on a laptop are so-called identical prefix collisions, which is where both prefixes are identical. More general chosen prefix collisions, where you have two different prefixes, is a much more expensive type of collision to compute. Stevens et al. Took 28 hours on a cluster of PS3s when computing the rogue TLS-CA certificate. And when we started our attack, it took a few dozens of hours in order to carry out the collision, but we were able to optimize it to run in under 5 minutes on our cluster. And we sort of stopped trying to optimize it at 5 minutes because our proof of concept attack was against this Cisco ASA VPN box, where the maximum configurable client timeout was 5 minutes. But the attack parallelizes well, and getting it even faster is just a matter of spending more resources. The second challenge is that it's not enough to have a collision between a pair of valid radius packets. We need to actually trick the server into sending one of the packets verbatim. We need to get the server to include the reject gibberish in the access reject packet that it sends. And this is a challenge because the reject gibberish is this long, unstructured looking byte string, which it would be extremely lucky if the server just included this by chance. It would not happen. There is this beautiful attribute called proxy state that is exactly what we need here. The proxy state attribute is something you can include in a request that the standard says must be returned unmodified in the response. And in fact, if you include multiple proxy states in a request, they must be returned unmodified in the order that they appear. And the server is not allowed to interpret the contents of them as anything more than an opaque blob. It can't change its behavior based on the contents of a proxy state. And this is intended to be used by stateless proxies, where if you have a radius proxy For instance, on an eduroam network, you log into here, the UCSB wireless system, but you're logging in with credentials from your home institution. So there is a radius server here that is acting as a proxy and forwarding requests onto the radius server run by your home institution. So proxies do happen in practice, and proxy states are used in practice. And basically what happens is each proxy will append on a proxy state attribute, and then in the response, it will strip the proxy state attribute off. For us, we're going to use this to get it to echo the gibberish back to us verbatim. So this is kind of perfect. Our access request is going to have header nonce attributes. And as the very last part of the prefix, we're going to have the 2-byte header for a proxy state. Recall this is type length value. There's 1 byte that says what type of attribute this is, and 1 byte that says how long it is. So we have this 2-byte header that says the next thing appearing in this packet is a proxy state. And then we have our reject gibberish. So we can disguise it as a proxy state, and we know it'll be echoed back to us. I'm going to take a quick aside to talk about the internals of the Stevens et al. MD5 chosen prefix collision attack, known as hash clash. The internals of this are not necessary for understanding how our attack works, but they're interesting, so I'm going to talk about them here. The way the attack works is it keeps track of the internal state of MD5 during hashing. This is known as an intermediate hash value, or IHV. It's also sometimes called a chaining value. And for MD5, this is 4 64-bit words. The thing that we care about here is the difference in IHV between the pair of messages that we're hoping will eventually collide. Once DIHV is 0, that means the internal state of MD5 is the same when hashing both messages, which means we have a collision. In phase 1 of hash clash, this is known as the birthday stage. And here we compute gibberish blocks that will put DIHV into a nice subspace. In particular, the first 64-bit word should be 0, and the last 2 64-bit words should be equal. And this subspace ends up being nice to work in, and it is somewhat easy to remain in this subspace when we append future blocks. So in phase 2, we have a near collision stage where we repeatedly append blocks that will keep us in that subspace, but reduce the Hamming weight of DIHV. So the more gibberish blocks we add on, the smaller the Hamming weight will get, until eventually DIHV reaches 0, and we have a collision. We have a trade-off between the number of near collision blocks and how difficult each near collision block is. If we need to reduce the Hamming weight by a large amount with each near collision block, that means it's going to be harder to find each near collision block. So if we are trying to optimize our attack to run in less than 5 minutes, we want to have our gibberish be a certain length. So with that said, the maximum length of a proxy state attribute is only 253 bytes. There is 1 byte that says this is a proxy state. There's 1 byte that says here's how long it is. 1 byte has a maximum value of 255. There's 2 bytes for the header, so that's 253 bytes that you can fit your gibberish into in a single proxy state value. But the sort of optimal value for our attack is gibberish that's on the order of 400 bytes. So it won't fit into a single proxy state attribute. The solution to this is we can embed inside the gibberish the header for another proxy state attribute, and possibly yet another proxy state attribute. Recall, these headers are only 2 bytes. So what we can do is have 253 bytes of gibberish, and then in the near collision block that comes after, we'll fix the 2 bytes at the end of the first proxy state to be the 2 bytes that say the next attribute is a proxy state, and it too is 253 bytes long. And so on until we have the desired number of near collision blocks for our attack to be likely to succeed under 5 minutes. By doing this, we're able to split up the collision gibberish among numerous proxy states which lets the attack succeed in under 5 minutes. So let's go through an example. We start by triggering an access request, and we intercept it and take the nonce, which here is this 726 and so on. We then predict the following prefixes, which I'm realizing there should at the end of it be some attributes. We have our accept prefix, which starts with 02, meaning accept. It has our length of 1C0. And we have copied the nonce from the request into there, where the response authenticator computation will use it. And after this, we would have any attributes that we would like to forge in the request. For instance, exec privilege 4, if we want our victim device to give us higher privileges. And finally, we would have this 21 EC that are in this slide at the beginning of accept gibberish that say the next attribute is a proxy state whose length is 0xEC. After that, we compute a chosen prefix collision that will find gibberish blocks we can append onto the end of the accept prefix and the reject prefix that will give us a collision. So here you can see it starts with the 21 EC should be part of the prefix, but you can see in the middle, we have a second proxy state that has 21 C0, where we have a second proxy state of length C0. After that, we can send an access request where we are using the nonce from the original access request and the reject gibberish. And when what we get back will be an access reject that will contain a proxy state attribute with our reject gibberish. We get the response authenticator from that access reject, and we can put it onto the access accept. Now this packet is going to have a valid response authenticator, and thus will be accepted by the victim device. Because of the collision, they're going to both be accepted by the device. OK, so if any of you are already familiar with Radius, probably the first thing that you're going to ask is, well, you said that this is all happening over UDP, but what about EAP TLS? This is a great question. And it turns out the TLS in EAP TLS does not protect Radius at all. Instead, what we have in EAP TLS, EAP, of course, being the extensible authentication protocol, which you can use to support authentication modes beyond just a simple password. What we have for EAP TLS is Radius is wrapping EAP, which is wrapping TLS. The TLS does not wrap Radius. This is something that is intended not to protect the Radius traffic, but rather it's intended to provide a secure channel between the user and the server, such that the user can authenticate to the server without the device being able to eavesdrop on the password. For example, for Eduroam uses, I forget if it's EAP TLS or EAP TTLS, but it uses one of these modes so that you can trust that your password is only going to be sent securely to your home institution's Radius server, rather than needing to worry that it will be eavesdropped on by UCSB network administrators, if that's something that you're worried about. Which means that the access accept packet is not sent over TLS. It is sent over UDP, which means our attack should still work against it. Except the one thing that is preventing this attack from working against Eduroam is that the EAP standard requires that any Radius packet that includes an EAP message, so it is carrying EAP traffic, must have a separate attribute called message authenticator. And message authenticator uses not MD5, but HMAC MD5 to authenticate the packet contents. And HMAC MD5, similar to Sandwich MAC MD5, is not known to be vulnerable currently. So a Radius client receiving an access accept, access reject, or access challenge with a message authenticator present must calculate the correct attribute. This does get checked by the client, and although it's not on this slide, any message that contains an EAP message must contain the message authenticator attribute, or it will be dropped. So the thing that's preventing us from attacking Radius carrying EAP TLS is not the TLS, it is HMAC MD5. So to summarize the impact of the blast radius attack, radius modes PAP, CHAP, and MS-CHAP are all vulnerable. EAP modes are likely not vulnerable because of the message authenticator. It may be possible to strip off the EAP message from our access accept or access reject, which is something that it is implementation dependent how that will be responded to. If you get an access accept that does not carry an EAP success, some standards say you should treat that as a success. However, actual implementations, we haven't found any that do yet. So it seems that it's probably fine for now, but may depend on the implementation. If you are running radius over UDP over the open internet, you are almost certainly vulnerable. A horrifyingly large number of entities are running radius over UDP over the open internet. However, because we require a machine in the middle on the network, this means that if you're running radius over a VLAN or an IPsec tunnel, then you're not going to be able to attack that unless you already have access to the network. But this could still be useful for pivoting from having network access to having compromised every device that uses radius within an organization. And in terms of timing, as mentioned, our proof of concept takes around 5 minutes. Actual implementations generally have timeouts of around 1 minute if multi-factor authentication is involved. It can't really be reduced below that without failing some legitimate users, because multi-factor authentication takes a while to take out your YubiKey and plug it in, that sort of thing. So reducing timeouts below 1 minute isn't really feasible. But as our attack parallelizes well, it would be possible to get our time even lower by just spending more resources than we did, or even by implementing the hash clash attack in hardware. In terms of mitigations, this was kind of interesting because it feels like there's an easy mitigation, which is don't use MD5. But the story is a little more complicated. There are over 90 vendors involved in this mitigation process. And it turns out backward compatibility is a major requirement. Radius is running in windmills and power plant controllers and devices that are very difficult to upgrade. There are even vendors who have done hardware implementations of MD5 for computing these even faster. So any mitigation that we recommend needs to be something that is not going to break compatibility with these unupdatable clients. So in conversation with these vendors, what we've come up with as a mitigation is to take in the short term, the already standardized HMAC MD5 based message authenticator, which is required for EAP, but currently optional everywhere else, and to make it mandatory, to have all responses and all requests include the message authenticator, and to have both clients and servers verify the message authenticator. Of course, in the long term, the answer is just wrap it in TLS so that you can get the confidentiality and integrity guarantees that TLS already provides the radius lacks. There was an attempt to standardize this around 10 or 12 years ago that ended up stalling. There is, based on this research, a current draft of radius over TLS that is actively being standardized right now. So I will conclude with this relevant XKCD. That is our presentation, and I'm happy to take any questions. Thank you.
As we did before, if you have any questions, raise your hands and we will get a mic to you. We have plenty of time for questions.
So as you explained, it seems to be an attack that is very difficult to mitigate. Would maybe counter cryptanalysis be an option here for current deployments?
This is a great question.
I can also pass the phone to Mark to answer if that's the...
No. This is a great question. In particular, one thing that you would think would be a really easy mitigation is if you see any bizarre proxy states, then you should just drop the packet. This turns out not to be workable for reasons that I have on a backup slide. But the short of it is, in one direction, proxy states do actually appear in real radius traffic, because, as mentioned, there are proxies that are used in the real world, and it's used to prevent proxy loops. But in the other direction, it turns out we don't actually need to use proxy state specifically. We can, if we want, use some vendor-specific attribute that is not proxy state in our access accept packet that goes to the client. And clients, if they see a vendor-specific attribute that they don't recognize, they just ignore it. It doesn't make sense to reject a response packet based on it including a vendor-specific attribute that you don't know, because there are a huge number of vendor-specific attributes. And then on the reject side, there are other places where it's a little more difficult than proxy state, but where we can still get that echoing behavior. So one example that we have here is if you make the username contain the string you'd like to be echoed. There is depending on the implementation, there's a good chance that in the error message that you get as a reply, it will include the username verbatim. And as long as you're able to predict what an access reject will look like, this is something that you can use to put the gibberish that you want into the packet. So looking for proxy states is something that seems like it might be a good mitigation, but turns out not to actually work in practice. Does that answer your question?
No, it doesn't, but I'm happy to see the backup slide, so, right?
So I can say that sort of counter cryptanalysis for SHA-1 is very fast, and we can give some guarantees on security of repaired SHA-1 basically. For MD5, it's several hundred times slower than regular MD5, and we can't give guarantees yet. So I don't think anybody wants to really do counter cryptanalysis for MD5 in practice.
Thanks. So that does answer my question. Yeah.
Awesome.
Suggest for people who aren't symmetric cryptanalysts, you might explain counter cryptanalysis. You know, the idea of the looking at the attacks, everything. So go ahead, you know, or we could make Mark do it.
Yeah, I'm going to defer that to Mark because I'm also not an expert in symmetric cryptanalysis.
I'll hand the phone back to Mark.
Yeah, sorry. So counter cryptanalysis, sort of like virtually the same concept as counter espionage. So it's basically detecting cryptanalytic attack in real time. And it basically is like, okay, for collision, you need to have two messages that collide. But counter cryptanalysis detecting the attack actually works if you just get one of the collisions. So you can do it in practice. And we show how this can be done efficiently for SHA-1 with only a factor 2 cost. But MD5 is so weak, you can attack it in so many ways. You have to check so many things that it really becomes 100 times slower than regular MD5. And it really has not been exhaustively explored, all these attacks. So we don't even can give any guarantee that you're actually missing something. But yeah, that's basically the concept. Real-time detection of cryptanalytic attacks. Yeah.
All right, well, we're waiting for other questions. Not many people have the good fortune of doing a responsible disclosure with that many vendors. I'm wondering if you have any additional stories you can tell or any lessons learned from doing such a massive coordinated disclosure.
Yes, yeah. The disclosure process, actually, we disclosed through CERT, which made the process go much smoother than we thought it would. So definitely recommend going through CERT if you have a disclosure process that's going to involve a huge number of vendors. And yeah, in terms of funny stories that happened during disclosure, we had a disclosure date set, and one organization that shall not be named here ended up having us push that back by over a month. So that was a little bit exciting. But no, I think most of the disclosure process was very informative for us, just in terms of we learned a lot about all of the different places that MD5 is actually deployed. Sorry, that Radius is actually deployed. The the fact that basically every piece of networking equipment made in the last 25 years supports radius was news to us. We knew it was used in only a few places, but yeah, so that was a really cool thing that we learned in our conversations with affected vendors.
Yeah, actually, I had a question about that, it being supported in so many devices. When you say that, do you mean that they have special facilities for processing radius messages that flow through them? Or do you mean it's used to admin those devices themselves?
Used to admin those devices. They're acting as a radius client.
Right.
This is sort of, if you imagine that you want to deploy a whole bunch of access points, and you want to be able to log into these things and administer them across an entire campus. And I'm not talking about connecting to the Wi-Fi network, I mean administering the actual devices. This is something where it really doesn't make sense to store authentication credentials on every single access point. So instead, organizations will have one central radius server that all of these devices will be set up to talk to that server to decide if an attempted login into the device should be allowed or not. So this is actually quite common at large organizations.
Hello, thank you for the great talk. You mentioned that among the vulnerable modes of radius is the combination with MS shop. Have you ever tried to attack like MS shop mode EDROM? Because I know at least of one university that uses that instead of DTLS.
So EDROM, and in fact, any WPA enterprise network is going to be using radius as part of 802.1x. So there is this, so in 802.1x, that is using EAP. And inside of EAP, there can be an inner authentication mode, which is sometimes MS-JAP. But for 802.1x specifically, in the final EAP message that is sent as part of an access request, or sorry, as part of an access accept, there's information in that EAP message that includes cryptographic keys that are then used for the connection. So even if we were able to drop the EAP message and the message authenticator from that access accept, even if like an implementation didn't throw up its hands and throw an error, if that happened, we wouldn't be able to get the keys that are then needed to actually do anything interesting with that connection. So even if the device says that it's willing to grant us access to this 802.1x network, we don't have the encryption keys needed to do anything on it. So EDROM is, fortunately or unfortunately, depending on how you look at it, not vulnerable to our attack.
Makes sense, thank you.
While you were, I gather, discovering that radius was much more widely deployed than you'd expected, did you come across hints of any other surprising protocol or thing that's used all over the place that almost nobody in this room knows about?
Yeah, there actually are a few things that still use MD5 apparently. One of them is, so it's possible to use MD5-based signatures for authenticating TCP connections. This is something that is apparently still used for securing some BGP sessions. So this is something that may be interesting to look at in future work.
I think we have time for one more.
So one of your potential mitigations is to encapsulate the radius in something like DTLS, whatever. But that seems to me, if you can't change a client to fix the MD5, now you have to change the client to support DTLS, which seems even worse, harder.
This is why it's sort of a long-term mitigation. In addition to standardization, it's more difficult to roll out. One thing I will say, though, is that it's possible to terminate TLS at something that you put in front of industrial controller that you can't get firmware upgrades for, and terminate TLS that way.
All right, let's thank Adam one more time.
And so now that we learned that Radius is broken for authentication, in case you're thinking to switch to Kerberos for authentication, I have very bad news for you. Because the next talk is called Windows into the Past, Exploiting Legacy Crypto in Modern OS's Kerberos Implementation. This talk is going to be given by Michal Shagam. She is a PhD student of Eyal Ronen at the Tel Aviv University. And her research focuses on analyzing real-world cryptographic implementations and side channel attacks. And this attack was actually under embargo until last Wednesday. So it's, so to say, fresh off the press. And it was presented at Usenix last week, and now we have it here. Whenever you're ready, feel free to take it away.
Oh, the presenter, thank you. Okay, awesome, thank you. Well, as Miro said, I'm Michal. I'm a PhD student at Tau University under the supervision of Eyal Ronen. And I have really bad news about Kerberos, which, by the way, also has MD5 in it, but that's not what we exploited. But it's another issue with legacy crypto. I'm going to tell you a little bit about our paper, Windows into the Past, and talk to you about the process, the different issues that we encountered and how we dealt with them. And so, well, we broke Kerberos. This you pretty much know. And Kerberos is supported by Windows, Mac, and Linux. Windows has a closed source implementation. And for Mac and Linux, there are two very common implementations, including MIT and Heimdall. Mac uses Heimdall. It switched about a few years ago. And Heimdall was actually introduced because they wanted to not be bound by the export regulations in the US for crypto. And Kerberos is used by universities, hospitals, and even government and military organizations. So it's pretty prevalent. And we took the Bleichenbacher attack and we made it significantly more practical enough in order to implement an end-to-end impersonation attack on Windows. And Windows, as you know, is pretty much used everywhere. And so what's the Kerberos protocol? Well, it's also an authentication protocol for non-secure networks. Different entities on the network need to be able to know that they're actually speaking to each other and not to some machine in the middle. And Kerberos provides secure communication between them and secure access to services, or at least it's meant to. I think it's stuck. Okay, no. Okay, so if we take a simplified look at Kerberos, well, a user that wants to perform different actions, for instance, logging into the domain or accessing remote files, remote printers, remote PowerShell sessions, and even accessing remote emails with the Outlook Exchange, they need to perform Kerberos authentication. So the user would enter their password into the client would perform the Kerberos authentication for them. And after that, the user would have access to the resources. And the password is not sent as plain text. There is a one-way function that relies on the password. So the situation isn't that bad. But passwords are susceptible to different attacks like dictionary attacks, database breaches, phishing attacks. If you've seen the movie Spaceballs, then you know that 1, 2, 3, 4, 5 was the choice for both a luggage combination and the air supply. And this was a very, very bad choice. I hope that you know it's a bad choice even if you haven't seen the movie. And luckily for us, a lot of smart people put their heads together in 2006 and decided to extend the Kerberos protocol and support not just symmetric crypto, but asymmetric crypto as well, and two-factor authentication using smart cards. Smart cards are physical tokens, like the YubiKey mentioned before. And these tokens support cryptographic operations that are performed on the smart card itself, and they can also store credentials. So the user can use can use the smart card, forego the password, and perform the Kerberos authentication using a smart card that only requires a simple PIN like 1, 2, 3, 4, 5, 6. So the smart card gives us two-factor authentication because we use a PIN code, which is something we know. And we also have physical access to the smart card, which is something that we have. And so we got rid of the passwords. So our system should pretty much be secure, right? Who thinks it's secure? Well, along came an attacker that noticed that the smart card was using RSA with a padding scheme that is vulnerable to the Bleichenbacher attack. These attackers were me and Eyal. And we were happy, but everyone else should be sad. And so the KCS1 version 1.5 padding scheme is vulnerable to the Bleichenbacher attack, which has been around for over 25 years. And since then, we have seen many different reincarnations of it. There's the Bleichenbacher attack, and after this came the Munger attack, which was actually for a different padding scheme, but can be adapted to the same padding scheme. And there were additional attacks, such as the drone, the robot, the Marvin, and Bleichenbacher's cat. And these attacks mostly focused on protocols such as SSL and TLS. But we haven't seen any attacks on Kerberos. And since Kerberos is so prevalent, this begs the question, why? Well, it's not that easy to find a padding oracle for Kerberos. First of all, when the requests are sent, the connection simply times out, even if the decryption is correct, and even if it's not, it simply times out. So there aren't any error messages that we can rely on. In terms of timing analysis, the decryption, unfortunately for us, actually happens after the connection times out. And in addition to this, we mentioned that the decryption is performed on the smart card itself, meaning we can't attack it with microarchitectural side channels. And so RSA decryption can also be modeled in layers: the mathematical layer, the unpadding, and the protocol level handling. And we already know that since the private key cannot leave the smart card, the mathematical layer is performed on the smart card itself. But luckily for us, in a lot of cases, the unpadding and protocol level handling occur on the client itself. And then we can attack the unpadding layer or the protocol layer with microarchitectural side channels. And so what we did is we looked at different distributions and implementations of Kerberos. We looked at Windows and the two open source implementations. And we noticed that MIT did implement Bleichenbacher mitigations, but Windows and Heimdall did not. In addition, the smart card interface can also sometimes perform unpadding. And we noticed that the OpenSC implementation was also non-constant time. And for a system, for configuration to be not vulnerable, well, both components need to be constant time. Otherwise, we can target the one that isn't. We still chose to go with Windows because Windows was closed source, so it made it a lot more fun. And so we started reverse engineering Windows, and we found several different functions to focus on, including this one. This is basically how my screen looked for about a few months, let's say. And here's an example of a function that we focused on. So the CPE import key initially unpads the decryption, the decrypted message. And if it's successful, if the padding is conforming, then it performs additional tasks, including using the decrypted message in order to decrypt the rest of the packet. Meaning we perform two different actions only if we are successful with the unpadding. So we have a function that is non-constant time that we can target for our padding oracle. And so we chose to focus on non-constant time code in the unpadding layer, and we used the flush and reload cache attack technique in order to perform this. While it gave us a solution, it was still very noisy, and we had to deal with that later. And so for the Bleichenbacher attack, what do we actually need? Well, we need a padding oracle with feedback, which we have. And we also need to be able to modify the ciphertext. And since we're running on a non-secure network, there can be a router or other machine in the middle, which we can compromise that will allow us to modify the ciphertext. In addition, the Bleichenbacher attack is also known as a million message attack, meaning in order to perform it, we need to send a lot of different messages, a lot of queries. It is also not a key recovery attack. We don't actually recover the private key. We can only use it to recover a single instance of the a single encrypted message. And in the case of Kerberos, this is a token that has a lifetime of 10 hours. So we need to be able to send a lot of different messages and to do this in under 10 hours, which doesn't sound like a lot of time. It sounds like a lot of time, but basically it's not, at least not at the rate that we can send the queries. And so what are the different ways that we can generate messages? Well, when a user uses the computer and logs in, they also generate Kerberos authentication requests. And they also do this when they access remote files. In addition, if they want to access their remote emails on the Exchange server, they also need to generate a request. We noticed that while for the login, we needed to enter the PIN code to use the smart card, we didn't need to do this for remote files and other actions. And so what we decided to do is we decided to use a harmless looking malicious site and use the browser in order to access remote files. We were able to hide these requests and the error messages from the user. So we had a stealth attack, and we also utilized the repetition mechanism by refreshing the HTML several times at a constant pace, generating repeated queries. And so initially, our attack intercepted the messages that the server returned. And although the server didn't attempt to detect the large amount of authentication requests, we still wanted to make sure that the server wouldn't be able to do this in the future. And we noticed that the Kerberos message included a lot of unauthenticated data. And so we tried to spoof the entire response packet, and we were able to do so. So we decided not to send the request messages to the server, but to completely respond as the server itself. Therefore, the KDC was also unaware of our attack. And so we introduced a browser with a harmless looking malicious site that the user would access, which would generate the queries at a very fast pace without requiring the user to perform these actions. If we had relied on the user to perform the actions that would generate queries, we would likely pass the 10-hour deadline. Now, the question is whether this is fast enough. And the short answer is that it's sometimes fast enough and only for some of the messages. And we created a simulated perfect oracle and we ran it on a database of real tokens, 40,000 to be exact, that were generated by the KDC. And we found that for a quarter of the messages, we were able to decrypt them in under 20,000 queries, and for about a tenth in under 10,000. And this is great, but this is for a perfect oracle, and our oracle is actually not, it's noisy. Luckily, we don't need to decrypt all the messages. We only need to decrypt one of them. Once we decrypt one message, we can use the token in order to request access to all of the user or admin's resources, meaning we can also have privilege escalation easily. And so let's look at the Bleichenbacher attack a little bit more closely. From the padding structure constraint, we get a range for the possible range for the original message. And the first stage of the algorithm is to find an initial multiplier. And using this initial multiplier, we can further reduce the range. The second stage of the attack is a little bit faster and reduces the range with every additional multiplier found. So positive results help us reduce this range until we can recover the original message. I can give you a lot of different reasons for why the oracle will be noisy, technical reasons, but basically it's kind of like eating cookies and it gets really, really messy and really fast. There are false positives, there are false negatives, and as shown before, the range is only reduced for positive results, meaning our attack can handle false negatives. We can't really handle false positives, and we would like to reduce this probability as much as we possibly can. One way of doing this would have been to repeat all the queries, but there's no need to do that. And traditional methods repeat only the positive ones, only the positive results, but we wanted to improve this. So what we did is we took a second look at our oracle and we realized it wasn't actually binary. And we would only need to repeat some of the results, including the result of 1. And for results of 2 and above, we wouldn't actually need to perform the repetition. We created a tailored repetition algorithm instead. We ran this attack and we focused on a subset of messages, which was 18% of the messages, which were fast, which we could decrypt fast with our oracle. And we performed one attempt for each of 17 tokens that were in this subset. We were successful for 15 of them, but for 2 of them, we encountered false positives. So we realized that we would need to detect these false positives after the fact in order to save time. When we looked at the distribution of the amount of queries after in the second stage of the attack, we noticed that we had an upper bound, meaning that if we had too many false results in a row, we had probably encountered a false positive. And since our state had changed, we needed to be able to perform a traceback. And so we created the traceback attack recovery, where we saved previous states and we counted the amount of false results. And then if we encountered a false positive, we reverted to one of the previous states. By doing this, we were able to reach results that were much closer to that of the perfect oracle. We were able to decrypt over 40% of the messages in under 10,000 queries. And traditional methods, as you can see here, require a lot more queries, and we don't necessarily have this time, especially not with a noisier oracle. And so we're left with another question. Which messages belong to the fast subset? How can we detect them without a perfect oracle? Well, we noticed that there's actually a correlation between the 2 attack steps, and that a fast initial search would lead to a fast reduction, a range reduction. We used this in order to classify the different messages, and for messages that weren't fast, we could abort early. We performed this attack for 3 days, and we found 3 messages that were fast, and we were able to detect and decipher each one of these messages in under 20 hours, which is less than a day. So basically, what we saw was that we found non-constant time implementations that led us to side channels. We also saw that there is a lack of forward secrecy, which can compromise other protocols. And we also weren't limited in the amount of RSA decryption attempts that we had. And it's not really clear why we weren't limited, because we don't need this many authentication attempts in real life. So the ghost of crypto past continues to haunt us here and allowed us to break the Kerberos protocol and also implement the much more practical Bleichenbacher attack and use it for an end-to-end impersonation attack on Windows. So we had one PIN code entry, one harmless looking malicious site, and after one day, we got full control. Thank you.
Get the mics, it's on the recording.
So the plot for the attack success rate showed with the traceback method, it's still not converging to 1. Do you know what the remaining instances were, why it was failing?
Yes, I cut them off a little bit earlier on. In these cases, there were situations where the initial multiplier that we found were problematic, and we implemented further on an additional improvement for this.
Nice talk, thanks. Did you use the attack which was, also the improvement of Bleichenbacher's attack, which was at crypto, I don't know, 2010, 12? Were you based on that one, also because you didn't mention it?
No, so what we did to improve the Bleichenbacher attack, well, we implemented a lot of the different optimizations, but we basically focused on the original Bleichenbacher attack. And in addition to this, we allowed it to handle noisy oracles. We can further improve this, but I don't think that the results would have been significantly different in this case. I think that most of the impact was the additional traceback and also the detection of the false positives, and also the detection of the fast subset, looking at the different distributions and how the how the attack behaves in the 2 different stages of the attack and how they are connected. This was the addition that we added.
For the multipliers, you take only integers, not fractions.
What?
The multipliers you use in the RSA, you take only integers or also fractions? Because if you use fractions.
Yes, there's another optimization which uses fractions and reduces it on the other end. We didn't implement this. We did look at this, but I don't think that it would have improved the attack significantly, because after we found the initial multiplier, then the attack was a lot faster. The range reduction stage is significantly faster.
I mean, it's for the first step mostly where you need it.
Yeah, the first step is the one that requires a lot of attention, especially when looking at the different oracles. And if it's a noisy oracle and you miss if you have a false negative in the initial stage, it's problematic to continue the attack. Luckily, we can just move on to the next token in our case. But if you have a false positive, then you also kind of miss the token and you need to continue. So we wanted to make sure that we could give every single message the best shot, because not all of the messages were fast enough to be able to decrypt in under 10 hours.
Okay.
We had a rate that allowed us to perform about 16,000 queries. And obviously other setups might require might be able to perform less. And we wanted to implement an attack that would be able to help people perform it on slower machines or at a different rate as well.
Okay, thanks.
Yeah, so not many people have the fortune of doing coordinated disclosure on such a widely deployed protocol. I'm wondering if you have any stories that you can share about that process or any lessons that you learned.
Yes, so we began the process almost a year ago, I guess. And the embargo was until last Wednesday when Usenix began. And most of the people that we spoke to had a lot of good ideas. They also suggested additional vendors in some cases, or contacting IETF. And we had meetings with some of the vendors and suggested mitigations. As mentioned for Radius, we also suggested the mitigation of using TLS and basically more modern protocols, because the issue was that we use legacy protocols here, legacy crypto for a protocol that is significant and is used in a lot of different places. I've also seen that it's used in combination with Radius, so it's not really an option to replace one with the other. But yes, the different vendors also mitigated quickly. They added the mitigations and patched things, and we waited for one of the vendors that had a lot of different clients to also finish patching, and I think the process was successful in the end. Yeah.
All right, let's thank Mikhail another time.
Okay, and with that, we have a bit of longer break. We will continue here 5 minutes before 4 p.m. So please make sure to be back in time. For the next talk that we will have after the break, so far we looked at attacks on cryptography, meaning a vulnerability found in cryptography. And then we saw an explanation of how one can break this cryptography. In the next talk after the break, we will see an attack that actually happened in practice, and we will see the case study of how this attack happened and bypassed end-to-end encrypted messaging. So this will be a very special and interesting talk, and I hope you'll come back for that. Have a good break.